more number theory in this section. 4.3, primes and greatest common divisors. A key definition, two definitions next. An integer is prime if it's at least 2 and its only factors are itself and 1. And an integer is composite if it's also at least 2 and not prime. Alright, so any integer 2 or higher is either prime or composite. Why are we starting at 2? Well, the integer 1, it's a kind of a special case. Yeah, it's the identity for multiplication, so it has that special property. If you multiply anything by 1, it stays the same. Anyway, the terminology says that 1 is not prime and not composite. Yeah, using our divides notation, remember A divides B is written like this. It just means A is A divides N. A is a factor of N. So for any integer n greater than or equal to 2, to be prime means that if any A positive integer divides n, then that A has to be 1 or n itself. Okay, if you have a composite integer, then it could have more divisors, but primes only have two factors. And so listing all the integers from 2, well, as far as 12, we can see the primes, so they're highlighted here. So yes, 2 and 3 are prime. 4 is not prime, it has a smaller factor 2 in there. 5 is prime, 6 is not prime, so 6 is composite. It has factors besides 1 and 6, it has 2 and 3. 7 is prime, 8, 9, 10 are composite. Yeah, 9's an odd number, but it's not prime. Has a factor of 3. 12, yeah, every even number except for 2, every even number is composite. Okay, so primes and composites, probably quite familiar to you. Example 1, factor 140 into a product of primes. Okay, so that's kind of the main importance of primes is they're kind of the building blocks for all numbers. So from 140, well, let's see how we can break it up into factors as small as possible. Well, you could do it this way. So starting with 140, yeah, it's 14 times 10. Yeah, any number ending in 0 is going to have 10 as a factor. 14, that's not a prime number. That breaks up itself into 2 times 7. And we try to break up 2, but 2 is a prime number, so no smaller factors. The same for 7. On this side, 10. Yeah, 10 is composite. It's not prime. It breaks up into 2 times 5. Okay, so on the bottom here, these circled numbers, these are the prime factors. Okay, so putting these together, yeah, usually we'll start with the smallest. So we have 2 times 2 times 5 times 7. Alright, so yeah, we've just broken 140 into smallest possible factors. Maybe there's a different way to break this up. Suppose instead of 14 times 10, you did 2 times 70. 2 is prime, but 70 breaks up. You could do 7 times 10 or 2 times 35 here. 35 is 5 times 7. Alright, so yeah, we got the same prime factors, 2 times 2 times 5 times 7, in a different order, but yeah, starting with the smallest. Okay, so this is called a prime factorization of 140. And a key thing to realize about integers, every integer, at least 2, can be factored uniquely. Okay, so putting them in order, so every integer can be factored uniquely into a product of primes. Yeah, that's called a fundamental theorem of arithmetic. Yeah, it's certainly fundamental. So that's why primes are important, so that you can break down any number into simpler pieces, and these primes are the simplest possible pieces. I mean, yeah, you could write 140, it's 4 times 5 times 7, but 4 is not prime, so yeah, we want the prime factorization. Yeah, this up to ordering just means, yeah, we could also write this as 5 times 2 times 2 times 7, but we're not counting that as a different factorization. It's really the same primes there. Let's see some more examples. Example 1 here, yeah, the integer 7 is prime because its only factors are 1 and 7. 9 is composite because it's divisible by 3. Building blocks, yes. Example 2, yes, some more prime factorizations. Again, you could find these using that factor tree idea. Yeah, these kind of look like upside down trees, slightly. Okay, so 100, you could break it down the same way. You get 2 times 2 times 5 times 5, or 2 squared times 5 squared. If you try to break 641 into smaller pieces, you'll find there are no smaller factors, so 641 turns out to be prime. We'll see how to prove things like that. 999, 999. You could break that up as 9 times 111, and then I see here, yeah, 111 is 3 times 37, 9 is 3 times 3. Try to break up 37, it turns out 37 is prime, no smaller factors. So the prime factorization of 999 is 3 times 3 times 3 times 37. Again, we put them in order from smallest to largest. And 1024, yeah, that's 10 2's multiplied together. So yeah, that's 1K. Yeah, some more examples. Find the prime factorization of 539. Yeah, so these bigger numbers, yeah, it's not so easy. So the smallest prime is 2, so is 2 a factor? No, so that's not an even number if it ends in 9, so 2 is not a factor. Maybe 3. Okay, so here we're doing it by hand. We could use a calculator. So 3 into 539. So doing a long division, yeah, it goes in 179 times, but there's 2 left over. So it's, yeah, 179 and 2/3, so you'll get 179.666 repeating. Either way, 3 is not a factor. 3 does not divide 539. Yeah, 5 doesn't work either. For 5 to divide a number, it has to end in a 0 or a 5. Okay, so we're kind of working our way through this list of primes. 2 is not a factor, 3 is not a factor, 5 is not a factor. Let's try 7 next. And thankfully 7 does work. So 539, it's 7 times 77, no remainder. So that gets us started in the factor tree. 7's prime, but 77 breaks into these factors, and these 2 are prime. Okay, so we found the prime factorization, 7 times 7 times 11. Yeah, it's a good idea to check. So multiply these numbers, check, yeah, you do get 539. Okay, one more. Find the prime factorization of 541. So we'll use our same method. Start with the small primes. So if you divide 541 by 2, 2 is not a factor because the remainder is 1. Divide by 3, the remainder is 1. So 3 is no good. Divide by 5, the remainder is 1 again. This time 7 doesn't work either. 541 divided by 7 has remainder 2. Okay, so we're working our way through all these primes, and we're getting remainders that are not 0. Okay, so that tells us that none of these primes, as far as 23, none of these primes are factors. So do we have to keep checking all the primes up to 541? The good news is no. So the square root of 541 is 23 point something. So that's telling us, yeah, if 541 is a product of two numbers, then these two numbers can't both be bigger than 23. At least one of them would have to be 23 or less. Does that make sense? Yeah. So if you have, say, 24 times 24, that's going to be bigger than 541. So if 541 is a product of two smaller numbers, in other words, if 541 is a composite, then one of those smaller numbers has to be 23 or smaller. And in particular, if, say, the A is the small one, then either A is prime or a product of primes, but either way, there has to be a prime factor smaller than or equal to 23. Okay, if there's no such prime factor, yeah, so we've ruled out all the primes 23 or smaller, then that tells us that 541 has to be prime itself. So it's not composite. It doesn't have two smaller pieces, two smaller factors. So what's the prime factorization of 541? Well, it's just one number. It's the prime 541. Just like the prime factorization of 7 would be just 7. Alright, so yep. So the moral of that story, so in general, if n is a composite number, then it must have a prime factor that is less than or equal to the square root of the number. And conversely, if you've checked all the prime factors up to the square root and none of them divide n, then n must be a prime number. Okay, so checking to see if a number is prime, then yeah, just check the primes up to as far as the square root. That's as far as you need to go. Okay, yeah, so that's what this theorem says. Example 3, show that 101 is prime. Okay, so the square root of 101 is 10 point something, so the only primes less than or equal to 10 are 2, 3, 5, and 7. Okay, 2 doesn't divide 101. 3, try 3, that doesn't work. 5 doesn't work. Divide 101 by 7. Well, 7 into 10 goes once. Subtract, that's 3. 7 into 31 goes 4 times. Remainder 3. So 7 is not a factor either. So 101 is a prime number. And one more. Find the prime factorization of 700. Let me read that correctly. 7007. Yeah, so we can see 7 is going to be a factor. So making our factor tree, yeah, that's 7 times 1001. And 7 is prime. Okay, then we have to work on this piece, 1001. Okay, yeah, start dividing by primes. 2, 3, and 5 don't work, but if you divide by 7, 7 is a factor. So just reading here, yeah, it goes in 143 times. Okay, we found 2 7s, those are prime. So those parts are finished. 143, is that a prime number? It turns out, yeah, 143, it's 11 times 13. Okay, yeah, so starting 2, 3, 5, 7, 11 is the first prime factor, and it goes in 13 times. Alright, 11 and 13 are prime, so we finished. So that's the prime factorization of 7007. Alright, so yeah, you can have fun with this if you're bored. Yeah, take any integer and break it down into its prime factors. Okay, those prime factors are unique, and every integer 2 or higher can be broken down like that. Okay, yeah, so these prime numbers, they have a long history. They've been studied for thousands of years, going back to the ancient Greeks and beyond. Though, yeah, it's certainly, we're already seeing that it's definitely an advantage to have a calculator or a computer if you're working with bigger numbers. The sieve of Eratosthenes is one way to find prime numbers kind of systematically. Okay, it's an ancient Greek mathematician. So how does it work? Well, you start with a list of numbers, say as far as you want to go, say up to 30. So start by circling 2, the first prime number, and remove all its multiples. Okay, so 2 times 2, 3 times 2. Okay, so we're removing every even number bigger than 2. And what's left? Well, circle the next number, that happens to be 3, and remove or cross out every multiple of 3. Okay, so 2 times 3, that's already crossed out. 3 times 3, 4 times 3, 7 times 3, 24, 9 times 3. Yes, every multiple of 3, that's not going to be prime. The next number is 5. Cross out the multiples of 5. These are already crossed out, except, 25 we need to cross out. Next, 7. Cross out the multiples of 7, 21, 28. Eleven is next. Cross out 22. 13. Cross out 26. It's already crossed out. 24. And yes, everything else is prime here. Okay, yeah, so this it's not a very efficient way to find primes, but it certainly works. So yeah, just at each stage, so circle the next number and cross out its multiples. Okay, yeah, so that's this famous sieve. Yeah, it's like you're kind of sieving, and the composite numbers fall through the sieve. You're just left with the primes. So what's the biggest prime? Well, the largest known prime is this big number. Yeah, try putting this in your calculator. So 2 multiplied by itself 82 million and some times, minus 1. All right, yeah, don't forget the minus 1. Without that minus 1, then this is definitely not prime. It's 2 times 2 times 2, and so on. But yeah, so this number is not going to work on your calculator. It's got millions of digits. Okay, yeah, so this is the largest known prime, found in 2018. But I'm sure they'll find a bigger one soon. It's every few years they find a new one. Sometimes it makes the papers. Primes of the form a power of 2 minus 1 are called Mersenne primes, after Marin Mersenne. Yeah, it turns out it's easier to check numbers that look like this to see if they're prime than other numbers. So how do we know that this isn't the biggest prime? Well, it turns out, the Greeks knew that in fact there are infinitely many primes. So that sieve of Eratosthenes, that's going to go on forever. Those circled numbers. Here is the man himself, Eratosthenes. Yes, he's actually from Egypt, which was a Greek colony at the time. Yeah, this is 200 BC. And here's a bigger list going up to 100. But yeah, the same idea, just circle each number and cross out its multiples. And yeah, this is a famous old theorem. There are infinitely many primes. Let's take a quick look at the proof. So yeah, we're not really doing proofs, but this is a classic. And since we've looked at logic, so the idea is to, well, assume that there are only finitely many primes, so P1, P2, up to Pn. Then construct this number q, so it's the product of those finitely many primes plus 1. Okay, we know by the fundamental theorem of arithmetic that this number q must have a unique prime factorization. So either q itself is prime, or it can be written as a product of two or more primes. Okay, but the problem is, yeah, none of these primes P1 through Pn can divide q, because yeah, if P divides q, well, we know P divides this piece, so if P divides q, let's say P sub j, if P sub j divides q, we know P sub j divides this piece. So if you look at the difference, P sub j has to divide 1, which is not possible. Okay, so none of these finite number of primes divide q. Okay, so that contradicts the fundamental theorem of arithmetic. Okay, so the problem arises when you assume there are finitely many primes. Yeah, you end up with a contradiction. So that assumption has to be wrong. So consequently, there are infinitely many primes. Example 5, looks at some more Mersenne primes. So 2 to the power 2 minus 1, that's 3, that's a Mersenne prime. 2 to the power 3 minus 1 is another Mersenne prime. 2 to the 5 minus 1. 2 to the 7 minus 1 is 127. Yeah, you can check that's also prime. You see a pattern, so the powers themselves are primes, but 2 to the power 11 minus 1 is 2047. That's composite. Alright, so yeah, not every number 2 to the power of prime minus 1 is a prime. And here is Mersenne. Yeah, French. Alright, so next we'll look at greatest common divisors. So divisors, that's just another name for factors. Yeah, we're just interested in positive divisors. So looking at 10, so the divisors of 10. So what numbers divide 10? What positive numbers? So just 1, 2, 5, and 10. Okay, so yeah, we're not looking at prime factors now. We're looking at all factors. So 1's not prime, 10's not prime, but we're looking at all the numbers that divide 10. How about 18? So the divisors of 18, it has more divisors: 1, 2, 3, 6, 9, and 18. Okay, so then we could ask, what's the biggest divisor they have in common, these two numbers? Well, they have divisor 1 in common, so yeah, every two numbers. So 1 is always a divisor, so that's always going to be common. They have a 2 in common. There's a 5 here, but no 5s, no 10s, so nothing else in common. So the greatest common divisor of 10 and 18 is 2. All right, so that's the idea. So the greatest common divisor, yeah, we're using this notation, GCD 10, 18 in parentheses. Yeah, another common name is the greatest common factor. Maybe you're used to the GCF. So you also see this notation. And in math papers, yeah, if the context is clear, then yeah, certainly number theory papers, this means the greatest common divisor. In this example, find the GCD of 42 and 70. Well, for the first solution, yeah, we could do it the same way. It's kind of labor intensive. So 42, yeah, 1 is a factor. 2 times 21. 3 is a factor. 3 times 14. 6, 7, 14, 21, 42. Yes, hopefully we've got them all. Yeah, these are the factors of all the factors of 42, all the factors of 70. Okay, so we see 1 is a common factor, 2 is a common factor, 7 is a common factor, but the greatest common factor is 14. So that's the GCD we're looking for here for these two numbers. All right, so if the numbers aren't too big, you could certainly find the GCD this way, but a more efficient way is to use the prime factorizations of the two numbers. Okay, so maybe make a factor tree. So 42 is 6 times 7, 6 is 2 times 3. So 42 is these factors. 70 is 7 times 10, 10 is 2 times 5. So this is the prime factorization of 70. And how can we use these factorizations to get the GCD? Well, now we're looking for common factors. So yeah, they both have 2's. They both have 7, so just 1 7 and 1 2 in common. So the GCD is 2 times 7. Alright, so yeah, we're just looking for common factors. So the greatest common factor, the greatest common divisor, looking at it this way, so looking at the prime pieces, it's 2 times 7. Okay, so we get the same answer. Yeah, we saw 1 is always going to be a common factor, but sometimes it's the only common factor. So in that case, we say two numbers are relatively prime. For example, 14 and 33 are relatively prime. So yeah, that means they have no factors in common except for 1, and their prime factorizations must use different primes. Yeah, 14 is 2 times 7, 33 is 3 times 11. So yeah, they're using different primes. Okay, and let's look at the Euclidean algorithm. Yeah, this is one of the oldest and most famous algorithms. It's also very efficient. Yeah, it gives a very good way to find the greatest common divisor of two numbers. And it's based on the division algorithm we looked at. So remember, the division algorithm says if you divide A by D, you get a quotient Q and a remainder R. And you can write it like this. So A is equal to D times Q plus R, and that remainder has to be between 0 and D minus 1. So the remainder is positive or 0, but it has to be smaller than the number you're dividing by. Alright, so why is this useful for finding greatest common divisors? Okay, so here's how it works. So let's say we want to get the GCD of A and B. Yeah, we want to assume that A is greater than or equal to B, so we're just putting the bigger number first. And so step 1 is to divide A by B and get the quotient, let's call it Q sub 1, and the remainder R sub 2. Okay, so by the division algorithm, so we're dividing A by B, so A is equal to B times the quotient plus the remainder, and we know the remainder has to be less than the B we're dividing by. Okay, then the clever part is to now take that second number B and divide it by this new remainder. Okay, so B divided by the new remainder. Yeah, that new remainder has to be less than B, so we are dividing by a smaller number. We get a quotient, and the new remainder, R sub 3, where R sub 3 is strictly less than R sub 2. And we just keep doing that. So now that r sub 2 is going to get divided by the new remainder, r sub 3. We get a new quotient and a new remainder, r sub 4. Okay, and you see what's happening. These remainders, they're getting smaller, so r sub 3 is strictly less than r sub 2. r sub 4 is strictly less than r sub 3. They can't go negative, they have to stay positive, so these remainders get sandwiched. So this procedure has to finish with a 0 remainder. These are integers, of course, so they can't keep getting closer to 0 without actually hitting 0. And the algorithm, the procedure says that the last non-zero remainder is the GCD we're looking for. Okay, so yeah, it's a bit complicated. Also, yeah, keeping track of these indices, but the idea is, so we're looking for the GCD of two numbers, a greater than or equal to b. Well, divide the big number by the smaller number, get a remainder. Divide the smaller number by that remainder to get a new remainder. Then divide the first remainder by the latest remainder to get another remainder. And just keep doing that. The remainders have to get to 0, and the last non-zero remainder is the GCD. Yeah, we kind of get a slightly nicer pattern if you call a r sub 0 and b r sub 1. Then it's r0, r1, r2, r1, r2, r3. Okay, so you can do it that way. Alright, so example 5, use the Euclidean algorithm to find the GCD of 18 and 10. So yeah, we did this already, but let's do it with the algorithm. Again, putting the bigger number first. So that's the a, or the r sub 0, that's 18. r sub 1 is 10. Okay, so divide 18 by 10. You get 1, remainder 8. Okay, so 10 goes into 18 once, with 8 left over. Now divide 10 by that remainder. So 8 goes into 10 once, remainder 2. Now divide 8 by 2. It goes in 4 times with no remainder. Okay, so yeah, these remainders have to get smaller. They have to eventually hit 0, and the last non-zero remainder is the GCD. Yeah, so like we found earlier, the GCD is 2. Alright, so yeah, we're not explaining why it works, but it does work. Okay, yeah, there's more material. Yeah, lots of open questions about primes. And here's the Euclidean algorithm. Yeah, Euclid, another Greek. And here's that same procedure. So to find the greatest common divisor of r sub 0 and r sub 1, divide r sub 0 by r sub 1, get the quotient and remainder r sub 2, and then divide r1 by r2 to get r3 in remainder. Keep doing that. These remainders get smaller. At the nth step, when you divide by this remainder r sub n, you get a 0 remainder on the next line, so then the GCD is r sub n. So let's do one last example. Find the greatest common divisor of these two bigger numbers, 414 and 662. Yeah, so you can see if you were going to do it using our earlier methods, so listing all the divisors, that could be a lot of work. Even finding the prime factorizations is going to be some work. But for the Euclidean algorithm, you don't need to find any factors. Okay, so we just divide 662 by 414. It goes in once, remainder 248. Then divide 414 by 248. Okay, yeah, it just goes in once, remainder 166. And now divide 248 by 166, remainder 82. Okay, so these remainders getting smaller. 166 divided by 82. Okay, now we're making some progress. That goes in twice, remainder 2. And then 82 divided by 2 goes in 41 times, remainder 0. So this was the last non-zero remainder, so the GCD is 2. Okay, yeah, so maybe these had, factors of 13s, 29s, but the Euclidean algorithm avoided any factoring. It's just dividing in remainders. All right, so that's some good number theory.